close your eyes, and let's drift backward through time, back through history, through the formation of Earth, through the birth of our Sun, back to the very beginning of everything. Our journey begins 13.8 billion years ago, in a moment so profound it defies imagination. The Big Bang, not an explosion into empty space, but the sudden emergence of space itself, of time itself, of everything that would ever exist. In that first instant, all the matter and energy in the entire universe was compressed into something smaller than an atom, infinitely hot, infinitely dense. And then, in a fraction of a second so small we have no everyday comparison for it, the universe began expanding, and it has been expanding ever since, growing larger with each passing moment, carrying galaxies away from each other like raisins in rising bread dough. Let yourself relax as we consider what happened in that first second. The universe went through more dramatic changes in its first second than it has in all the 13.8 billion years since. In the first trillionth of a second, the fundamental forces that govern our universe, gravity, electromagnetism, and the nuclear forces, separated from each other, taking on their distinct identities. By the end of the first second, the universe had cooled from its initial infinite temperature to about 10 billion degrees Fahrenheit. In that brief moment, the basic rules of physics that still govern reality today were established, the cosmic stage was set, and the story of everything began to unfold. Now breathe slowly and picture the universe just 3 minutes after the Big Bang. It had cooled enough for the first atomic nuclei to form, mostly hydrogen and helium, with tiny amounts of lithium. This process, called Big Bang nucleosynthesis, created the first matter in the universe. These primordial elements still make up about 98% of all ordinary matter in the universe today. Every hydrogen atom in your body, every hydrogen atom in water, every hydrogen atom in every star, all were created in those first few minutes after the Big Bang. You carry within you particles that are nearly as old as time itself, witnesses to the birth of the universe. As you sink deeper into tranquility, consider what came next. For the first 380,000 years after the Big Bang, the universe was opaque, a hot, dense fog of particles and radiation where light couldn't travel freely. Then, as the universe expanded and cooled, electrons and protons combined to form the first complete atoms. At this moment, light could finally travel through space without being scattered. This ancient light, released when the universe was just 380,000 years old, has been traveling ever since. Today, we detect it as the cosmic microwave background radiation, the afterglow of creation itself, visible in every direction we look, a faint whisper of radio waves that fills all of space. Here's something peaceful to contemplate. The cosmic microwave background radiation has a temperature of just 2.7 degrees above absolute zero, the coldest possible temperature. This radiation is incredibly uniform, the same temperature in every direction to within a few 10,000ths of a degree. Yet those tiny temperature variations are crucial. The slightly warmer spots indicate regions where matter was slightly denser in the early universe. These tiny density differences, imprinted when the universe was less than a year old, were the seeds from which all structure would eventually grow, the galaxies, stars, and planets, all traced back to quantum fluctuations in the first fraction of a second, amplified by cosmic expansion into the grand architecture of the universe we see today. Let your thoughts drift now to the dark ages of the universe, not a metaphor, but an actual period lasting about 100 million years when the universe was truly dark. The cosmic microwave background radiation had faded, but the first stars hadn't yet formed. During this cosmic night, only darkness and gravity existed, with invisible clouds of hydrogen gas slowly collapsing under their own weight. Imagine the universe during this time, vast, expanding, cooling, yet completely dark, waiting patiently for the first light to shine. As you breathe gently and deeply, consider the moment that darkness ended. About 100 to 200 million years after the Big Bang, in pockets where gas had collapsed to sufficient density, the first stars ignited. These were not stars like our Sun, they were massive giants, perhaps hundreds of times the mass of the Sun, burning brilliantly blue and living fast. These population 3 stars, as astronomers call them, were made entirely of primordial hydrogen and helium. In their cores, nuclear fusion created the first heavy elements, carbon, oxygen, iron, and all the others that would later make planets possible, that would eventually make life possible. These first stars lived only a few million years before exploding as supernovae, scattering their newly created elements across space. We've never directly observed a population 3 star, they're all long gone, but we know they must have existed because we see their legacy in the elements that fill the universe today. Now, as you settle into deeper relaxation, picture the first galaxies beginning to form. Gravity pulled matter together into increasingly larger structures. Small clumps of stars merged into larger collections. By about 500 million years after the Big Bang, recognizable galaxies existed, islands of stars separated by vast dark spaces. These early galaxies were smaller and more chaotic than modern galaxies, constantly colliding and merging, growing through cosmic violence into the majestic structures we see today. The universe was entering its adolescence, no longer the smooth, simple place of its infancy, but becoming complex, structured, interesting. Finally, let this gentle fact carry you toward dreams. Everything we've described, the Big Bang, the formation of atoms, the first stars and galaxies, all happened in darkness, or at wavelengths of light human eyes could never see. No observer witnessed these events. The universe's most dramatic transformations occurred long before anything existed that could appreciate them. Yet through science, through careful observation and brilliant reasoning, we've reconstructed this story. We've learned to read the universe's history in the light that reaches us, in the patterns of galaxies, in the faint whisper of the cosmic microwave background. The universe has kept a record of its own birth, written in light and gravity, waiting billions of years for something to evolve that could read it and understand. And finally, we arrived, looked up, and began to comprehend our cosmic origins. Rest now in this knowledge, floating peacefully through the early universe, where time itself was young, where the first light was just beginning to shine, and where the story of everything was taking its first steps toward the present moment. Breathe slowly and let yourself drift forward through cosmic time, as the universe continues its magnificent unfolding. Let us journey now to understand the scale of the observable universe, the sphere of space from which light has had time to reach us. The observable universe is approximately 93 billion light-years in diameter. This seems impossible at first. If the universe is only 13.8 billion years old, shouldn't we only be able to see 13.8 billion light-years in each direction? But the universe has been expanding while light travels through it, stretching the distance. Objects that emitted light 13.8 billion years ago have since moved much farther away due to cosmic expansion. We see them as they were in the ancient past, but they now exist in a present we can never observe, at distances we can never reach. As you relax even deeper, consider what lies beyond the observable universe. The universe doesn't end at the edge of what we can see, it almost certainly continues far beyond, perhaps infinitely. There may be billions or trillions of galaxies beyond our cosmic horizon that we will never see because light from them hasn't had time to reach us yet. In fact, due to the accelerating expansion of the universe, there are galaxies we can see now whose light will never reach future observers billions of years from now. The universe is not only vast beyond imagining, but most of it is forever hidden from us, unknowable, existing beyond the boundaries of what we can ever observe. Let your thoughts drift to dark matter, the mysterious substance that makes up approximately 85% of all matter in the universe. We cannot see dark matter, it doesn't emit, absorb, or reflect light. We know it exists only through its gravitational effects. Galaxies rotate too fast to be held together by the gravity of their visible matter alone. Something invisible must be providing additional mass. Galaxy clusters show the same problem. When astronomers map the total mass of a galaxy cluster using gravitational lensing, they find far more mass than can be accounted for by stars, gas, and dust. This invisible dark matter outweighs all the ordinary matter in the universe by more than 5 to 1. Everything we can see, every star, every planet, every galaxy, is just a small fraction of what exists. Now breathe gently and picture dark energy, even more mysterious than dark matter. Dark energy makes up approximately 68% of the total energy content of the universe. In 1998, astronomers discovered that the universe's expansion is not slowing down, as gravity should cause it to do, but is actually accelerating. Galaxies are flying apart faster and faster. Something is pushing space itself apart, working against gravity. We call this dark energy, but in truth, we don't know what it is. It's one of the greatest mysteries in all of science, yet it dominates the universe, determining its ultimate fate. As you sink into deeper tranquility, consider what these discoveries mean. The universe is made of 3 main components. Ordinary matter, the stuff of stars, planets, and us, makes up only about 5% of the universe. Dark matter accounts for about 27%. Dark energy comprises about 68%. This means that 95% of the universe is made of things we don't understand, things we can't directly detect, things that remain profoundly mysterious despite decades of research. We are like children who have just learned to read the first page of an enormous book, slowly beginning to comprehend that there is far more we don't know than we do know. Here's something peaceful to contemplate. Despite all this mystery, the universe follows comprehensible laws. The same physics that governs how a ball falls on Earth also governs the motion of galaxies billions of light years away. The same atoms that make up your body are the same types of atoms found in the most distant galaxies. The universe, though vast and strange, is fundamentally knowable. Every mystery we encounter is a puzzle we can potentially solve, not through magic or divine revelation, but through careful observation, creative thinking, and persistent effort. Rest now in this expanding cosmos, where the known and unknown dance together, where mystery and understanding coexist, and where the universe reveals itself slowly, patiently, to any mind willing to look in wonder. Let yourself drift deeper still, as we explore the structures that fill our universe, the cosmic architecture built from gravity and time. Drift with me now to understand galaxies, those magnificent islands of stars scattered throughout space. Our universe contains approximately 2 trillion galaxies, though this number is just an estimate based on what we can observe. Each galaxy contains millions, billions, or even trillions of stars. Some galaxies are spiral-shaped like our Milky Way, with graceful arms curving outward from a central bulge. Others are elliptical, shaped like footballs or spheres, containing mostly older stars in more random orbits. Still others are irregular, without clear structure, often distorted by gravitational interactions with neighboring galaxies. These 2 trillion galaxies represent 2 trillion separate communities of stars, each with its own history, its own structure, its own story stretching back billions of years. As you breathe slowly and peacefully, consider our home galaxy, the Milky Way. We live inside it, so we see it as a band of light stretching across the night sky, our edge-on view of the galactic disk. The Milky Way is a barred spiral galaxy, about 100,000 light-years across, containing between 200 and 400 billion stars. If you could view it from outside, you would see a beautiful spiral structure with several major arms and a bright central bar of stars. Our solar system resides about 26,000 light-years from the galactic center, in a minor spiral arm called the Orion Spur. We're in the suburbs of the galaxy, far from the crowded, energetic galactic core, in a relatively quiet neighborhood where conditions allow for the slow, stable evolution of solar systems like ours. Let your thoughts drift to the center of the Milky Way, where something massive and dark lurks. At the heart of our galaxy sits Sagittarius A*, a supermassive black hole containing about 4 million times the mass of our Sun, compressed into a region smaller than Mercury's orbit. Scientists have watched stars orbit this invisible monster, racing around it at thousands of miles per second, their motion revealing the presence of something massive yet unseen. This supermassive black hole, like those found at the centers of most large galaxies, played a crucial role in galaxy formation. The relationship between galaxies and their central black holes is intimate. They seem to grow together, influencing each other's development in ways we're still working to understand. Now breathe gently and picture the space between galaxies, the intergalactic medium. This isn't truly empty space but is filled with an extremely tenuous gas, mostly hydrogen, at a density of about 1 atom per cubic meter. This gas is heated to temperatures of millions of degrees by energy from galaxies and quasars, creating a hot, diffuse plasma that pervades the cosmos. Through this thin medium, galaxies move like ships through a cosmic ocean. Even the voids, the emptiest regions of space, contain this whisper-thin gas, ensuring that no place in the universe is truly, absolutely empty. As you sink into deeper tranquility, consider the cosmic web, the large-scale structure of the universe. Galaxies aren't randomly scattered through space but are arranged in vast filaments and sheets, surrounding enormous voids where almost no galaxies exist. This structure looks remarkably like a spider's web, with clusters of galaxies at the intersections and long strands connecting them across hundreds of millions of light-years. The voids between can be 300 million light-years across, regions of space containing very little, dark and empty. This cosmic web is shaped by dark matter, whose gravity pulls galaxies into these patterns, creating the largest structures in the universe, patterns so vast it takes mapping millions of galaxies to see them. Here's something beautiful as you relax even deeper: galaxies collide. Unlike stars within a galaxy, which are so far apart that stellar collisions are extremely rare. Galaxies are close enough together relative to their size that galactic collisions are common on cosmic timescales. When galaxies collide, they don't crash like solid objects. Instead, they pass through each other, their stars safely navigating the vast spaces between other stars. But their shapes distort dramatically, stretched and warped by gravitational forces, sometimes creating tidal tails of stars streaming out into space. Over hundreds of millions of years, the colliding galaxies merge into a single, larger galaxy. Our own Milky Way is currently in the process of consuming several smaller dwarf galaxies, and in about 4.5 billion years, we will collide and merge with the Andromeda Galaxy, creating a new, giant elliptical galaxy that future astronomers have already nicknamed Melkomeda. Rest peacefully now, floating among these island universes, these vast communities of stars, knowing that even galaxies, those seemingly permanent fixtures of the cosmos, are temporary, changing, evolving, colliding and merging in the slow dance of cosmic time. Breathe softly and let yourself drift to the stars themselves, those brilliant points of light that fill the galaxies and illuminate the darkness. Let us journey now to understand what stars truly are. A star is a massive sphere of plasma, held together by its own gravity, generating energy through nuclear fusion in its core. In the heart of a star, hydrogen atoms are compressed together with such force that they fuse into helium, releasing tremendous energy in the process. This energy radiates outward, creating the light and heat we see and feel. Our Sun is doing this right now, fusing about 600 million tons of hydrogen into helium every single second. Yet the Sun is so massive that it can continue this process for approximately 10 billion years total. It's currently about halfway through its life, having burned steadily for 4.6 billion years with about 5 billion years remaining. As you relax even deeper, consider the incredible variety of stars. Stars come in a vast range of sizes, temperatures, and colors. The smallest stars, red dwarfs, can be as little as 8% the mass of our Sun and glow dimly with a reddish hue. These tiny stars are incredibly efficient, burning their fuel so slowly that they can shine for trillions of years, longer than the current age of the universe. The largest stars, blue hypergiants, can be more than 100 times the mass of the Sun and thousands of times brighter. But these massive stars live fast and die young, exhausting their fuel in just a few million years. Between these extremes lie countless varieties: orange stars, yellow stars like our Sun, and everything in between, each type playing its own role in the cosmic ecosystem. Let your thoughts drift to the life cycle of stars, a story of birth, life, and transformation. Stars are born in nebulae, vast clouds of gas and dust where gravity slowly pulls material together. When enough mass accumulates, the core becomes hot and dense enough to ignite fusion, and a star is born. The star then enters its main sequence phase, the stable period where it fuses hydrogen in its core. This is where our Sun is now. Eventually, the hydrogen runs out, and the star enters its final chapters, which vary dramatically depending on its mass. Low-mass stars swell into red giants, shed their outer layers as planetary nebulae, and leave behind white dwarf cores. Massive stars explode as supernovae, leaving behind neutron stars or black holes. Every star follows this pattern: birth, stable burning, transformation, and finally, contribution of its material back to space, where it can be recycled into new stars, planets, and potentially life. Now breathe gently and picture a supernova, the spectacular death of a massive star. When a star much larger than our Sun exhausts its fuel, it can no longer support itself against gravity. The core collapses in less than a second, triggering a rebound explosion so powerful it briefly outshines an entire galaxy. For a few weeks, a single dying star can be brighter than 100 billion normal stars combined. These explosions are not just spectacular light shows, they're essential to the universe's evolution. In the intense heat and pressure of a supernova, elements heavier than iron are created. Gold, platinum, uranium, all the heaviest elements, were forged in supernova explosions. Every atom of gold in any jewelry, every heavy element in the Earth's core, was created in the death throes of ancient stars that exploded before our Sun was born. As you sink into deeper tranquility, consider that you are made of stardust, not metaphorically, but literally. The hydrogen in your body was created in the Big Bang, but every other element was forged inside stars. The carbon in your cells, the calcium in your bones, the iron in your blood, all were created through nuclear fusion in stellar cores. When those stars died, they scattered these elements across space. That material drifted through the galaxy, became part of new nebulae, and eventually condensed to form our solar system. The atoms in your body have extraordinary histories. Some were forged in red giants that gently puffed off their outer layers, others in violent supernova explosions. You are, quite literally, the universe made conscious, stardust that has organized itself into a form capable of contemplating its own origins. Here's something peaceful to contemplate as you drift toward deeper rest. Stars are not scattered randomly through galaxies but exist in a carefully maintained equilibrium. The pressure from the radiation pushing outward balances the gravity pulling inward, creating a stable sphere that can shine for billions of years. This balance is so precise, so delicate, yet so robust that stars maintain it throughout their entire main sequence lifetime. It's a reminder that the universe finds stability not through rigidity but through balance, not through permanence but through dynamic equilibrium, where opposing forces create lasting harmony. Rest now among the stars, those brilliant furnaces that transform matter and create the elements of existence, knowing that you carry within you the light of ancient suns, that you are connected to the cosmic cycle of birth and death and rebirth that has been unfolding for billions of years. Let yourself drift deeper into the cosmic tapestry, where we explore the remnants of stellar death and the most extreme objects in the universe. Drift with me now to understand neutron stars, the extraordinary remnants left behind when certain massive stars explode as supernovae. When a star's core collapses, it can compress matter to densities beyond comprehension. A neutron star is typically only about 12 miles across, roughly the size of a city, yet contains more mass than our entire Sunday. The gravity is so intense that a teaspoon of neutron star material would weigh about 6 billion tons on Earth. At this extreme density, protons and electrons are crushed together to form neutrons, creating a sphere of incredibly dense nuclear matter. The surface gravity is 2 billion times stronger than Earth's. If you somehow stood on a neutron star, you would be flattened to less than the thickness of a sheet of paper. As you breathe slowly and peacefully, consider pulsars, neutron stars that spin rapidly and emit beams of radiation from their magnetic poles. Some pulsars rotate hundreds of times per second, faster than a kitchen blender, despite being more massive than the Sun. As they spin, their radiation beams sweep through space like cosmic lighthouses. When one of these beams points toward Earth, we detect a pulse of radio waves, arriving with clock-like precision. The fastest known pulsar spins 716 times per second. That's a city-sized object with more mass than the Sun, rotating at a significant fraction of the speed of light at its equator. These cosmic timekeepers are so precise that astronomers once briefly wondered if they might be signals from alien civilizations before understanding their natural origin. Let your thoughts drift now to black holes, regions where gravity has become so extreme that not even light can escape. Black holes form when the most massive stars collapse, compressing their entire mass into an infinitely small point called a singularity, surrounded by an event horizon, the boundary beyond which nothing can return. Despite their reputation, black holes don't roam through space consuming everything like cosmic vacuum cleaners. They simply sit in place, and their gravity behaves like that of any other massive object. It's only dangerous if you venture too close. The event horizon of a stellar mass black hole might be only a few miles across, yet it contains the mass of multiple suns, creating a gravitational field so intense it warps space and time itself. Now breathe gently and picture supermassive black holes, the giants that lurk at the centers of most large galaxies. These monsters contain millions or even billions of times the mass of our Sun. The supermassive black hole at the center of the galaxy M87 contains about 6.5 billion solar masses. That's the equivalent of 6.5 billion suns compressed into a region about the size of our solar system. In 2019, astronomers captured the first-ever image of a black hole's shadow, specifically this beast in M87, showing the glowing ring of hot gas swirling around it, with the black hole itself silhouetted against the bright material about to spiral into oblivion. This image, assembled from observations by 8 radio telescopes around the world, showed humanity what a black hole actually looks like, confirming predictions made decades earlier. As you sink into deeper tranquility, consider what would happen if you fell into a black hole. From your perspective, you would cross the event horizon and continue falling toward the singularity. But something strange would happen. As you approached the black hole, the gravitational difference between your feet, closer to the black hole, and your head would become extreme, stretching you into a long, thin stream in a process astronomers whimsically call spaghettification. Meanwhile, to someone watching from a safe distance, time dilation would make you appear to slow down as you approach the event horizon, eventually appearing to freeze at the boundary, your image fading and redshifting but never quite crossing. From your perspective, you cross and fall in seconds. From their perspective, you never quite make it across, frozen at the threshold forever. Here's something both profound and peaceful: black holes may be the ultimate fate of all matter. In the unimaginably distant future, trillions upon trillions of years from now, after all the stars have burned out and matter has decayed, black holes might be the last remaining objects in the universe. But even black holes aren't eternal. Through a process called Hawking radiation, they slowly evaporate, leaking mass in the form of quantum particles. This process is incredibly slow. A stellar mass black hole would take longer than the current age of the universe to evaporate even a tiny fraction. But given enough time, timescales so vast they dwarf the current age of the universe by factors we can barely express, even black holes will eventually disappear, returning their mass and energy to the cosmos in the final chapters of the universe's story. Rest peacefully now, contemplating these extreme objects, these cosmic monuments to gravity's ultimate power, knowing that even the most extreme phenomena in the universe follow natural laws, that even black holes, those seeming destroyers of all things, are part of the natural cycle, playing their role in the cosmic story. Breathe softly and let yourself drift through the vastness of space and time, as we explore light, distance, and the fundamental nature of reality itself. Let us journey now to understand the speed of light, approximately 186,282 miles per second, or about 671 million miles per hour. This isn't just the speed at which light travels, it's a fundamental speed limit for the entire universe. Nothing with mass can reach the speed of light, let alone exceed it. This cosmic speed limit has profound implications. When you look at the moon, you're seeing it as it was 1.3 seconds ago. When you see the sun, you're looking back 8 minutes and 20 seconds. The nearest star beyond our sun, Proxima Centauri, appears as it was 4.24 years ago. Every object in the night sky is a window into the past, showing us not the present moment but history. The farther away something is, the further back in time we're seeing. As you relax even deeper, consider what this means for our understanding of the universe. When astronomers observe a galaxy 10 billion light-years away, they're seeing that galaxy as it existed 10 billion years ago, when the universe was much younger. The light carrying that image has been traveling through space for 10 billion years, crossing unimaginable distances to reach our telescopes. That galaxy as it exists today, its current state, its present moment, is forever hidden from us. We can never know what it looks like right now because information can only travel at the speed of light. In a very real sense, the present moment doesn't exist in astronomy. There is only the past, arriving at different times depending on distance, creating a view of the universe that is more like a history book than a photograph of the present. Let your thoughts drift to cosmic inflation, a brief but spectacular event that occurred in the first fraction of a second after the Big Bang. For an incredibly short period, perhaps 10 to the power of negative 32 seconds, the universe underwent exponential expansion, doubling in size approximately every 10 to the power of negative 37 seconds. In that brief instant, the universe grew from smaller than an atom to potentially the size of a grapefruit or larger. This rapid expansion solved several puzzles about the early universe, explaining why regions of space separated by vast distances have such similar properties. They were once close enough together to reach equilibrium before inflation pushed them apart. Inflation also explains the slight density variations we see in the cosmic microwave background. Quantum fluctuations stretch to cosmic scales, becoming the seeds from which all structure would grow. Now breathe gently and picture gravitational waves, ripples in the fabric of spacetime itself. Einstein predicted these waves in 1916 as a consequence of general relativity, but they weren't detected until 2015, when the LIGO Observatory recorded waves from two black holes spiraling together and colliding 1.3 billion light-years away. The detection measured a change in distance smaller than 1,000th the width of a proton, an almost impossibly tiny measurement, yet precise enough to detect the cosmic collision. Since then, we've detected dozens of these events, black hole mergers, neutron star collisions, and other catastrophic cosmic events. Gravitational waves represent a completely new way of observing the universe, allowing us to detect phenomena that produce no light at all, expanding our view of the cosmos beyond what electromagnetic radiation alone can reveal. As you sink into deeper tranquility, consider the nature of spacetime itself. Einstein showed us that space and time aren't separate things but are woven together into a four-dimensional fabric called spacetime. Massive objects cause this fabric to curve, and this curvature is what we experience as gravity. The Earth doesn't orbit the Sun because of some mysterious pulling force. Instead, the Sun's mass curves space-time, and Earth follows the straightest possible path through that curved space, which happens to be an elliptical orbit. This means gravity isn't a force pulling things together but a consequence of geometry, of the shape of space-time itself. We live not in empty space but in a dynamic, curved, flexible space-time that responds to matter and energy, bending and flexing under the influence of mass. Here's something both mysterious and peaceful: the universe might be flat. When cosmologists talk about the universe's shape, they're referring to its large-scale geometry. Measurements of the cosmic microwave background suggest that the universe is remarkably close to being geometrically flat, meaning that parallel lines remain parallel and the angles of triangles add up to 180 degrees, just as they do on a flat sheet of paper. This flatness is incredibly fine-tuned. If the universe had slightly different properties in its first moments, it would have either collapsed back on itself almost immediately or expanded so rapidly that structures like galaxies could never form. The fact that we exist in a flat universe that allows for structure formation is either an extraordinary coincidence or suggests something profound about the underlying nature of reality that we don't yet understand. Rest now in this curved space-time, where distance and duration are relative, where the past surrounds us in every direction we look, and where the universe reveals its deepest secrets through the patient observation of light and gravity. Let yourself drift even deeper into cosmic contemplation, as we explore planets, worlds, and the possibility of life beyond Earth. Drift with me now to the discovery of exoplanets, planets orbiting stars beyond our Sun. The first exoplanet orbiting a Sun-like star was discovered in 1995, and since then, astronomers have confirmed more than 5,600 exoplanets, with thousands more candidates waiting to be verified. These worlds come in astonishing variety. Some are gas giants larger than Jupiter, orbiting closer to their stars than Mercury is to our Sun, with surface temperatures hot enough to vaporize rock. Others are rocky super-Earths several times our planet's mass. There are water worlds covered in global oceans, ice giants, lava planets with one side perpetually molten, and planets orbiting binary star systems where two suns rise and set in alien skies. The diversity of worlds in our galaxy far exceeds anything we imagined before we began finding them. As you breathe slowly and peacefully, consider the habitable zone, the region around a star where conditions might be just right for liquid water to exist on a planet's surface. Not too hot, not too cold, but just right, like the story of Goldilocks. Earth sits comfortably in our Sun's habitable zone. Scientists estimate that there could be as many as 40 billion Earth-sized planets orbiting in habitable zones around Sun-like and red dwarf stars in the Milky Way alone. That's 40 billion potential worlds where liquid water might flow, where conditions could be suitable for life as we know it. Some of these worlds might be teeming with life right now, while others might be barren but habitable, waiting for life to emerge or arrive. In the vast tapestry of the cosmos, Earth may not be unique, but one of countless worlds where the conditions for life exist. Let your thoughts drift to the famous pale blue dot photograph, taken by Voyager 1 in 1990 from 3.7 billion miles away, at the edge of our solar system. At the request of astronomer Carl Sagan, the spacecraft turned its camera back toward home and captured Earth as a tiny speck, less than a single pixel, suspended in a beam of scattered sunlight. That pale blue dot contains everything we've ever known, every person who has ever lived, every civilization, every triumph and tragedy, every hope and dream. As Sagan wrote, everyone you love, everyone you know, everyone you ever heard of, lived out their lives on that mote of dust suspended in a sunbeam. This image provides profound perspective, a reminder of both our smallness in the cosmic scale and the preciousness of our fragile world. Now breathe gently and picture the Drake equation, a famous formula proposed by astronomer Frank Drake in 1961 to estimate the number of active, communicative civilizations in our galaxy. The equation considers factors like the rate of star formation, the fraction of stars with planets, the number of habitable planets per solar system, the fraction where life develops, and the fraction where intelligent life emerges and creates detectable technology. Depending on the values you assign to these unknowns, the Drake equation suggests there could be anywhere from 0 to millions of technological civilizations in our galaxy right now. The equation doesn't give us a definite answer, it's more a framework for thinking about the question, a way to organize our ignorance into categories we can study and refine. As you sink into deeper tranquility, consider the Fermi paradox, the puzzle and contradiction between the high probability of extraterrestrial civilizations existing and the complete absence of evidence for them. If the galaxy is billions of years old and contains billions of potentially habitable worlds, where is everyone? Why haven't we detected any signals, received any visits, seen any evidence of advanced civilizations? Various solutions have been proposed. Perhaps civilizations destroy themselves before achieving interstellar communication, perhaps they're deliberately staying quiet, perhaps the galaxy is simply too vast for signals to reach us yet, or perhaps, most sobering, intelligent technological life is incredibly rare, and we might be alone after all. The silence of the cosmos is one of science's deepest mysteries, teaching us humility about our place and purpose in the universe. Here's something peaceful to contemplate as you relax even deeper. Whether or not we find life elsewhere, Earth's biosphere represents something extraordinary, a planet where matter has organized itself into living systems, where chemistry has become biology, where evolution has produced consciousness and intelligence. For 3.8 billion years, life has persisted on this world, surviving mass extinctions, ice ages, asteroid impacts, and dramatic climate shifts. Life has proven remarkably resilient, adaptable, and creative, filling every available niche from deep ocean thermal vents to Antarctic rocks to the upper atmosphere. This tenacity, this persistence, this extraordinary complexity arising from simple chemistry, it's a reminder that the universe is not just a collection of dead matter and energy but contains within it the potential for something more, something that can observe, understand, and marvel at existence itself. Rest now in this universe of possibility, where countless worlds orbit distant stars, where life may flourish in forms we cannot yet imagine, and where humanity has just begun to ask the profound questions about our place in the cosmic story. Breathe softly and let yourself float through the gentle currents of cosmic time, as we explore the ultimate fate of the universe and the deep mysteries that remain. Let us drift now to the future of the universe, that vast expanse of time stretching ahead. Based on current observations, the universe will continue expanding forever, growing colder and darker with each passing eon. In about 5 billion years, our sun will exhaust its hydrogen fuel and begin to swell into a red giant, eventually engulfing Mercury and Venus, and possibly Earth. But this is just one small event in a much grander timeline. In trillions of years, all stars will have burned out, one by one, leaving galaxies as collections of dead stellar remnants, white dwarfs, neutron stars, and black holes, drifting through an increasingly cold and dark cosmos. This era, called the degenerate era, will last far longer than the current age of stars, a universe lit only by the occasional flare from colliding dead stars or matter falling into black holes. As you relax even deeper, consider what comes after even the dead stars fade. In timescales so vast they dwarf the current age of the universe, 10 to the power of 100 years and beyond, even black holes will evaporate through Hawking radiation. Eventually, the universe will reach a state of maximum entropy, sometimes called the heat death of the universe, where no energy is available to do work, no structure remains, and everything has reached the same uniform temperature just above absolute zero. The universe won't end in fire or ice, but in a slow fade to equilibrium, a cosmic evening that stretches into an eternal night. Yet this end is so incomprehensibly far in the future, a number with 100 zeros, that it's essentially forever. For all meaningful timescales, including trillions of years, the universe will continue to be interesting, dynamic, and filled with processes we can observe and study. Let your thoughts drift to the multiverse hypothesis, the idea that our universe might be just one of countless universes, each potentially with different physical laws and constants. Some theories in physics, particularly those dealing with cosmic inflation and quantum mechanics, suggest that new universes might constantly be forming, budding off from existing ones in an eternal, self-reproducing process. In some versions, every quantum event spawns new universes representing each possible outcome. These other universes, if they exist, would be forever separate from ours, unreachable and undetectable. The multiverse remains speculation, an idea that emerges from mathematical models but lacks direct evidence. Yet it raises profound questions about the nature of existence. If all possible universes exist, what does that mean for uniqueness, for fine-tuning, for our place in reality? Now breathe gently and picture the cosmic microwave background in more detail. This ancient light, released 380,000 years after the Big Bang, carries within it a treasure trove of information about the early universe. By studying tiny temperature variations in this radiation, differences of only a few millionths of a degree, cosmologists can determine the universe's age, composition, geometry, and fate. This light has been traveling for 13.8 billion years, carrying information about conditions when the universe was just beginning to form its first structures. The cosmic microwave background is essentially baby pictures of the universe, showing us what it looked like in its infancy, allowing us to trace its evolution from those early seeds to the rich tapestry of galaxies we see today. As you sink into deeper tranquility, consider the anthropic principle, the observation that the universe appears remarkably fine-tuned for the existence of life. If any of several fundamental constants, the strength of gravity, the mass of the electron, the cosmological constant, were even slightly different, stars couldn't form, or chemistry would be impossible, or the universe would have collapsed back on itself almost immediately after the Big Bang. Some see this fine-tuning as evidence of design or purpose. Others suggest the multiverse as an explanation. If countless universes exist with different properties, we naturally find ourselves in one of the rare universes where life is possible, because those are the only universes where anyone can exist to ask the question. Still others suggest we don't yet understand the fundamental principles that might explain why the constants have the values they do. The question remains open, hovering at the boundary between physics and philosophy. Here's something both humbling and peaceful: despite all our progress, we understand only about 5% of the universe. The other 95%, dark matter and dark energy, remains fundamentally mysterious. We've measured their effects, mapped their distribution, but we don't know what they actually are. Additionally, we lack a unified theory that reconciles quantum mechanics, which governs the very small, with general relativity, which governs the very large. We don't fully understand consciousness, the origin of life, or the ultimate fate of information that falls into black holes. The universe is still filled with profound mysteries, gaps in our understanding that represent not failures but opportunities. Every mystery solved reveals new questions, deeper puzzles. Science is not about achieving final answers but about continuously expanding the boundary of knowledge, always finding more to explore, always discovering that reality is stranger and more wonderful than we imagined. Rest peacefully now, floating through deep time, knowing that the universe's story is far from over, that mystery and wonder will persist for eons to come, and that even our ignorance is a gift, a reminder of how much remains to be discovered. Let yourself sink into the deepest peace now, as we explore the most profound questions about existence, consciousness, and the nature of reality itself. Drift with me now to consider the arrow of time, the mysterious fact that time seems to flow in only one direction, from past to future. On a fundamental level, most physical laws work equally well forward or backward in time. You could reverse a film of billiard balls colliding and it would look perfectly normal. Yet we experience time as having a definite direction. Eggs break but don't spontaneously reassemble. We remember the past but not the future. This arrow of time is intimately connected to entropy, the tendency of systems to move from order to disorder. The universe began in a highly ordered state at the Big Bang and has been increasing in entropy ever since. Time's arrow points in the direction of increasing entropy, from the structured past toward the more disordered future. This gives time its character, its irreversibility, its poignant quality. We move forward, always forward, unable to return. As you breathe slowly and peacefully, consider quantum mechanics, the physics that governs the behavior of atoms and subatomic particles. At the quantum scale, reality behaves in ways that seem impossible from our everyday experience. Particles exist in multiple states simultaneously until observed. They can tunnel through barriers that should be impenetrable. Two particles can be entangled, remaining mysteriously connected regardless of the distance separating them. Measuring one instantly affects the other, even across light years. Einstein called this spooky action at a distance and was deeply troubled by it, yet experiments have confirmed it's real. Quantum mechanics is the most precisely tested theory in all of science, making predictions accurate to 10 decimal places, yet nobody fully understands what it means. The math works perfectly, but the interpretation, what it tells us about the nature of reality, remains deeply mysterious. Let your thoughts drift to the measurement problem in quantum mechanics. Before you measure a quantum particle, it exists in what's called a superposition, multiple possible states at once. A particle can be in multiple places simultaneously, spinning in multiple directions at once. But when you observe it, when you measure it, the superposition collapses into a single definite state. The very act of observation seems to affect reality, forcing the quantum world to make a choice. This raises profound questions. What counts as an observation? Does consciousness play a special role in collapsing quantum states? Or does the universe constantly branch into parallel versions, with each possible outcome occurring in a different universe? These questions sit at the boundary between physics and philosophy, challenging our deepest assumptions about objectivity, reality, and the role of observers in the universe. Now breathe gently and picture the scale of the universe in terms we can almost grasp. If the sun were the size of a typical white blood cell, about 10 micrometers across, then the nearest star would be about 2,000 miles away. On this scale, the Milky Way galaxy would be about 70 million miles across, roughly 3/4 the distance from the real Sun to the real Earth. And the observable universe? It would be about 6 billion miles across, roughly the distance from the Sun to Pluto. These comparisons still involve numbers too large to truly visualize, but they hint at the extraordinary emptiness of space, the vast distances between objects, the breathtaking scale on which the cosmic drama unfolds. As you sink into deeper tranquility, consider that we are the universe observing itself. You are a collection of atoms that were forged in stellar furnaces, that drifted through space for millions or billions of years, that came together on Earth through chemistry and evolution to create a being capable of consciousness. Every thought you think, every emotion you feel, every moment of awareness, these are the universe becoming conscious of itself, matter organizing into patterns complex enough to contemplate their own existence. You are not separate from the cosmos but an integral part of it, a temporary pattern in the eternal flow of matter and energy, yet uniquely positioned to observe, understand, and appreciate the grand story of which you are both character and audience. Here's something both profound and peaceful: the universe seems to follow mathematical laws with extraordinary precision. Why should reality be mathematical? Why should the abstract concepts created by human minds match the deep structure of physical reality? The unreasonable effectiveness of mathematics, as physicist Eugene Wigner called it, remains mysterious. Perhaps mathematics is woven into the fabric of reality itself. Perhaps our minds evolved to recognize patterns that exist in nature because recognizing those patterns helped our ancestors survive. Or perhaps we notice only those aspects of reality that conform to mathematics, while ignoring the rest. Whatever the answer, the fact remains: the universe speaks the language of mathematics, and we have learned to understand that language, creating a bridge between mind and cosmos, between thought and reality, that allows us to comprehend our place in the grand scheme of existence. Rest now in this profound connection, knowing you are both infinitely small and infinitely significant, a brief spark of awareness in the cosmic dark, yet through that awareness participating in the universe's journey toward understanding itself. Breathe softly and let yourself dissolve into the gentle darkness, as we explore the final mysteries of our cosmic journey, bringing our story full circle. Let us drift now to consider the Hubble constant, which measures how fast the universe is expanding. For decades, this seemed like a straightforward measurement: determine how fast galaxies are moving away from us, and you know the expansion rate. But in recent years, a puzzling problem has emerged. When astronomers measure the expansion rate using nearby galaxies, they get one answer: about 73 kilometers per second per megaparsec. When they measure it using the cosmic microwave background radiation from the early universe, they get a different answer: about 67. These measurements shouldn't disagree, yet they do. This discrepancy, called the Hubble tension, suggests either our measurements have subtle errors we haven't found, or, more intriguingly, there's something fundamental about the universe we don't yet understand. Some unknown physics, some hidden component of reality, might be waiting to be discovered, a reminder that even our best established theories may be incomplete. As you relax even deeper, consider the cosmic horizon, the ultimate boundary of what we can ever know. Because light travels at a finite speed and the universe has a finite age, there's a limit to how far we can see. Beyond the cosmic horizon lies more universe, perhaps infinitely more, but it's forever hidden from us because light from those regions hasn't had time to reach us yet. Due to the universe's accelerating expansion, there are galaxies we can see now whose light will never reach future observers billions of years from now. They'll cross the horizon, disappearing from view forever. The universe is not only larger than we can see, but the visible portion is actually shrinking in terms of what will be observable in the deep future. We live in a privileged time, able to see evidence of the Big Bang and the universe's early history, evidence that will gradually fade as the universe ages. Let your thoughts drift to the cosmic calendar, a helpful way to comprehend the universe's timeline. Imagine the entire 13.8 billion-year history of the universe compressed into a single year. The Big Bang occurs at the stroke of midnight on January 1st. The first stars form around January 20th. The Milky Way takes shape in late January. Our solar system doesn't form until early September. Life appears on Earth in mid-September. Complex multicellular life emerges in mid-December. Dinosaurs appear on December 26th and go extinct on December 30th. All of human history, from the first Homo sapiens to the present, occupies only the final few hours of December 31st, recorded history. All of civilization, all of written language and technology, occurs in the last minute before midnight. On this scale, a human lifetime is a fraction of a second. This perspective both humbles and amazes. We are incredibly recent, yet we've achieved so much in our brief moment of existence. Now breathe gently and picture the overview effect, a profound cognitive shift reported by astronauts who view Earth from space. From orbit, national borders disappear. The atmosphere appears as a thin, fragile shell, thinner than the skin of an apple relative to its size. Earth seems small, delicate, isolated in the vast darkness, yet stunningly beautiful, a jewel of blues, greens, and whites hanging in the void. Astronauts describe this perspective as fundamentally transforming how they think about humanity and our place in the cosmos. Our differences seem smaller, our common humanity more apparent, our shared home more precious. This shift in consciousness is perhaps one of the greatest gifts of space exploration, seeing ourselves as we truly are, one species, one world, together on a small but precious planet, floating through an infinite cosmos. As you sink into the deepest tranquility, consider that every major question we've explored tonight connects to a single profound truth. We are part of something vastly larger than ourselves, yet we matter. The universe is 13.8 billion years old, 93 billion light-years across, containing trillions of galaxies with countless stars and planets. Against this scale, we are infinitesimally small, our lives briefer than a heartbeat in cosmic time. Yet we are also the part of the universe that can understand itself, that can trace its history from the Big Bang to the present, that can appreciate beauty, create meaning, and contemplate existence. The universe would exist without us, but it would go unwitnessed, unappreciated, unknown to itself. Through us, the cosmos becomes conscious, becomes curious, becomes capable of wonder. Here's something both final and peaceful. The universe is not a finished product but an ongoing story, and you are part of that story. Every breath you take exchanges atoms with the atmosphere. Every meal you eat incorporates matter from distant stars. Every thought you think represents the universe contemplating itself. You are not watching the cosmic drama from the outside but participating in it, inseparable from the whole, temporary yet essential. And when your brief chapter ends, the atoms that composed you will continue their journey, returning to Earth, perhaps eventually to space, maybe someday becoming part of other stars, other worlds, other forms of organization and complexity. Nothing is lost, everything is transformed. You are part of an endless cycle of matter and energy that has been unfolding since the beginning of time and will continue until the universe's final chapters, billions of years hence. Rest now in complete peace, wrapped in the knowledge of your cosmic heritage, cradled by the universe that made you, knowing you are both stardust and consciousness, both temporary and eternal, both infinitely small and infinitely precious. The universe continues its patient unfolding, and you are part of it, now and always. Let yourself sink even deeper into the cosmic embrace, as we explore the beauty hidden in the smallest scales and the dance of matter and energy. Drift with me now to the realm of atoms, those tiny building blocks of all matter. An atom is mostly empty space. If you could expand an atom to the size of a baseball stadium, the nucleus would be like a marble on the pitcher's mound, and the electrons would be smaller than grains of sand orbiting in the upper bleachers. Everything you see and touch, this solid world around you, is actually more than 99.9% empty space, held together by electromagnetic forces. You are made of emptiness and energy, organized into patterns that create the illusion of solidity. The table you rest upon, the ground beneath you, all are clouds of particles held in specific configurations by invisible forces, dancing in the void. As you breathe slowly and peacefully, consider that atoms are ancient beyond measure. The hydrogen atoms in your body were created in the Big Bang 13.8 billion years ago. The carbon atoms were forged inside stars that lived and died before our sun existed. Some of the atoms in your left hand may have been part of a completely different star than the atoms in your right hand. These atoms have been on extraordinary journeys, through the hearts of stars, through supernovae explosions, through interstellar clouds, through the formation of our solar system, through billions of years of Earth's history, through countless other living things before becoming temporarily part of you. You are not a fixed, permanent entity but a temporary pattern, a brief arrangement of ancient atoms that will soon continue their journey, becoming part of other patterns, other forms, other stories. Let your thoughts drift to the four fundamental forces that govern all interactions in the universe. Gravity, the weakest force, holds planets in orbit and galaxies together. The electromagnetic force binds atoms into molecules and is responsible for light, electricity, and chemistry. All of life depends on electromagnetic interactions. The strong nuclear force holds atomic nuclei together against the electromagnetic repulsion of protons, allowing atoms heavier than hydrogen to exist. The weak nuclear force governs radioactive decay and plays a crucial role in how stars shine. These four forces, acting together, create all the complexity we see, from atoms to galaxies, from crystals to consciousness. Everything that happens, every interaction, every change, results from these four fundamental forces operating according to simple, elegant mathematical laws. Now breathe gently and picture antimatter, the mysterious mirror image of ordinary matter. For every particle, there exists an antiparticle, an electron has a positron, a proton has an antiproton, and so on. When matter and antimatter meet, they annihilate each other completely, converting their mass into pure energy according to Einstein's famous equation E equals mc squared. This annihilation is the most efficient energy conversion possible, far more efficient than nuclear fusion or any other process. In the early universe, matter and antimatter existed in nearly equal amounts. But somehow, through a process we don't fully understand, there was a tiny excess of matter, about one extra particle of matter for every billion matter-antimatter pairs. When the universe cooled and the matter and antimatter annihilated, that tiny excess remained, becoming all the matter that exists today. Everything you see, every star, every planet, every living thing, exists because of this slight asymmetry in the early universe. As you sink into deeper tranquility, consider the Heisenberg uncertainty principle, a fundamental limit on what we can know about the quantum world. You cannot simultaneously know both the exact position and exact momentum of a particle. The more precisely you measure one, the less precisely you can know the other. This isn't a limitation of our measuring instruments, it's a fundamental property of reality itself. At the quantum level, particles don't have definite positions and momenta simultaneously, they exist in a fuzzy state of probability. This uncertainty is woven into the fabric of reality, ensuring that the universe always retains an element of mystery, of unpredictability, of openness to possibility. Even in principle, even with perfect instruments, there are things we cannot know with absolute precision. Here's something peaceful to contemplate as you drift toward deeper rest. The universe is not deterministic but contains genuine randomness at its heart. When a radioactive atom decays, when a quantum particle chooses one path or another, these events are truly random, not predictable even in principle. The future is not completely determined by the past. There's genuine openness, genuine possibility built into the structure of reality. This means the universe is not a clockwork mechanism grinding through predetermined motions, but something more alive, more creative, constantly generating genuinely new patterns and possibilities. The future is not written but is being created moment by moment, through the interplay of physical laws and quantum uncertainty, determinism and chance, necessity and possibility working together to create the rich, complex, surprising universe we inhabit. Rest peacefully now, knowing you exist at the intersection of order and chaos, law and randomness, being part of a universe that balances perfect mathematical structure with genuine creative possibility. Breathe softly and let yourself float through the final mysteries, as we explore the moments between moments and the infinite within the finite. Drift with me now to Planck time, the smallest meaningful unit of time in the universe, approximately 10 to the power of -43 seconds, a decimal point followed by 42 zeros and then a 1. Below this scale, our current understanding of physics breaks down completely. Space and time themselves become fuzzy, uncertain, governed by quantum effects we cannot yet describe. The Planck length is similarly tiny, about 10 to the power of -35 meters, far smaller than any particle we've detected. At these scales, the universe is a seething foam of quantum fluctuations, with virtual particles constantly popping into and out of existence, with spacetime itself becoming grainy and probabilistic. These scales represent the ultimate limits of the universe's resolution, the smallest canvas on which the cosmic painting is drawn. As you relax even deeper, consider that the vacuum of space is not truly empty but alive with activity. Even in the perfect vacuum of deep space, quantum mechanics ensures constant fluctuation. Virtual particle-antiparticle pairs spontaneously appear, exist for the briefest instant allowed by the uncertainty principle, then annihilate. This quantum foam permeates all of space, creating what's called vacuum energy or zero-point energy. These fluctuations have measurable effects. They slightly alter the energy levels of atoms in a phenomenon called the Lamb shift, and they create a subtle attractive force between metal plates in a vacuum called the Casimir effect. The void is not absence but presence, not nothing but potential, constantly vibrating with the possibility of existence. Let your thoughts drift to the concept of information in physics, which has become increasingly important in modern cosmology. Information, in the physics sense, refers to the complete description of a system's state, where every particle is, what every field is doing. According to the laws of physics, information cannot be destroyed, only transformed. But black holes seem to violate this rule. Anything falling into a black hole appeared to be lost forever, its information destroyed. This led to the black hole information paradox, which has occupied theoretical physicists for decades. Recent work suggests that information isn't actually destroyed but is somehow encoded in subtle correlations in the Hawking radiation emitted as black holes evaporate. The information escapes, but in a scrambled form that would take extraordinary effort to decode. The universe, it seems, keeps perfect records, loses nothing, maintains complete fidelity to its past even through the most extreme processes. Now breathe gently and picture the holographic principle, one of the strangest ideas in modern physics. This principle suggests that all the information contained within a volume of space can be encoded on the boundary of that volume, that the three-dimensional universe we experience might actually be a projection from information encoded on a two-dimensional surface. Imagine if everything you see, everything you experience, all of three-dimensional reality, was actually encoded on a distant two-dimensional boundary, like a hologram that creates the illusion of depth. This isn't science fiction but a serious theoretical principle that emerges from combining quantum mechanics with gravity. It suggests that the universe may have fewer dimensions than we perceive, that depth itself might be an illusion arising from information processing on a lower dimensional surface. As you sink into the deepest tranquility, consider the simulation hypothesis, the idea that our universe might be a sophisticated computer simulation created by an advanced civilization. This idea, popularized by philosopher Nick Bostrom, argues that if civilizations eventually gain the technology to create realistic simulations, and if they create many such simulations, then the number of simulated universes would vastly outnumber real ones, making it statistically more likely that we live in a simulation than in base reality. This hypothesis is unfalsifiable. There's no way to prove we're not in a simulation, but it raises profound questions about the nature of reality, consciousness, and existence. Whether we live in base reality or a simulation, the physics appears the same, the mathematics works the same, and the wonder we experience remains equally real. Here's something both strange and peaceful. The universe might be described by a wave function, a mathematical object that contains all possible states of every particle and field. According to some interpretations of quantum mechanics, particularly the many worlds interpretation, this wave function never collapses. Instead, it continuously branches into multiple versions, with each quantum event creating new parallel universes representing every possible outcome. In this view, there's a version of the universe for every possible quantum event that could have happened differently. Every decision you make, every random quantum event, creates new branches in the universal wave function. If this interpretation is correct, then in a very real sense, all possibilities are actualized somewhere in the multiverse of quantum branches, and the universe explores every pathway simultaneously. Rest now in this strange and beautiful reality, where the very small contains infinite complexity, where nothing is truly certain, where information is preserved eternally, and where reality itself may be stranger and more wonderful than any science fiction ever imagined. Let yourself dissolve into the gentlest peace, as we explore light, energy, and the bridges between science and human experience. Drift with me now to understand photons, the particles of light that connect us to the universe. A photon is a strange thing. It has no mass, yet carries energy and momentum. It travels at the speed of light, which means from a photon's perspective, no time passes at all. A photon emitted from a distant galaxy billions of years ago experiences no time during its journey to your eye. From its perspective, its emission and absorption are the same instant, an eternal now. When you see starlight, you're receiving photons that have traveled for years, centuries, or millennia, yet to those photons, the journey was instantaneous. Light exists in a timeless state, connecting distant places and times in a single moment, bridging the vastness of space with no subjective experience of the journey. As you breathe slowly and peacefully, consider that every photon of light is unique, carrying information about where it came from. The spectrum of light from a star tells us its temperature, composition, velocity, and age. The light from distant galaxies, redshifted by cosmic expansion, reveals how fast the universe is growing. The cosmic microwave background radiation shows us the universe as it was 380,000 years after the Big Bang. Every photon is a messenger, carrying news from distant places and times, and we have learned to read these messages with extraordinary precision. Astronomy is the art of listening to light, of extracting meaning from photons that have traveled across the cosmos to reach us, each one a tiny packet of information waiting to be decoded. Let your thoughts drift to the electromagnetic spectrum, the full range of light from radio waves to gamma rays. Visible light, the colors we can see, represents only a tiny sliver of this vast spectrum, less than 1%. We evolved to see this narrow band because it's the range of light that passes most easily through Earth's atmosphere and is emitted most strongly by our Sun. But the universe glows in all these wavelengths. Some galaxies emit primarily in radio waves. Nebulae glow in infrared. Supernovae flash in X-rays and gamma rays. By building telescopes that detect these invisible forms of light, we've expanded our vision to see the universe in ways human eyes never could, revealing phenomena that were completely hidden in visible light alone: black holes devouring matter, the birth of stars behind dust clouds, the afterglow of the Big Bang itself. Now breathe gently and picture the concept of luminosity, the total amount of energy a star or galaxy emits per second. Our Sun's luminosity is about 4 times 10 to the power of 26 watts, that's a 4 followed by 26 zeros. Every second, the Sun releases more energy than all of human civilization has produced in its entire history. Yet the Sun is just an average star. The most luminous stars can be millions of times brighter. Quasars, supermassive black holes actively feeding, can outshine entire galaxies, releasing as much energy as hundreds of trillions of suns. the universe operates on scales of energy that dwarf anything in human experience, yet follows the same conservation laws, the same physical principles that govern a candle flame or a flashlight beam. Energy can neither be created nor destroyed, only transformed. This fundamental law holds true from the smallest quantum interaction to the most energetic cosmic explosion. As you sink into deeper tranquility, consider redshift and blueshift, the stretching or compressing of light waves due to motion. When an object moves away from us, its light shifts toward the red end of the spectrum, longer wavelengths. When it moves toward us, light shifts toward blue, shorter wavelengths. This Doppler effect for light allows astronomers to measure velocities across cosmic distances. By measuring how much a galaxy's light is redshifted, we can determine how fast it's receding, and from that, how far away it is. The most distant galaxies we observe have their light stretched so much that ultraviolet light is shifted all the way into the infrared. These galaxies are receding at significant fractions of the speed of light, carried away by the expansion of space itself. In their light, we read the story of cosmic expansion, of a universe growing larger with each passing moment. Here's something peaceful to contemplate as you drift toward deeper rest. The night sky you see from Earth is different from the view from anywhere else in the universe. The specific arrangement of stars, their patterns and constellations, exist only from our vantage point. From a planet orbiting a star in another galaxy, the sky would be completely different, different patterns, different numbers of stars, perhaps viewing our Milky Way as a faint smudge in their sky. Yet the same physical laws operate everywhere. The same atoms exist throughout space. The same forces govern all interactions. While perspectives differ, while each location has its unique view, the underlying unity of physics ensures that the universe is fundamentally the same everywhere, a cosmos of infinite variety built on a foundation of elegant simplicity and universal law. Rest peacefully now, carried on waves of light across the cosmos, knowing that every photon tells a story, that light connects all things across space and time, and that the universe constantly sends us messages written in the language of electromagnetic radiation. Breathe softly and let yourself sink into the final depths of cosmic wonder, as we explore the moments that changed our understanding and the questions that remain. Drift with me now to the moment in 1929 when astronomer Edwin Hubble made a discovery that forever changed humanity's understanding of the universe. By measuring the distances to distant galaxies and their velocities, Hubble discovered that galaxies are moving away from us, and the farther away they are, the faster they're receding. This wasn't because we occupy a special position, it's because space itself is expanding, carrying galaxies apart like raisins in rising bread. This observation provided the first direct evidence for the Big Bang theory, showing that the universe hasn't always been as it is now, but is evolving, changing, expanding from a denser state in the past. Before Hubble, most scientists believed the universe was static and eternal. After Hubble, we knew we lived in a dynamic, evolving cosmos with a definite beginning and an ongoing transformation. As you relax even deeper, consider the cosmic calendar of discoveries that led to our current understanding. In 1915, Einstein published General Relativity, showing that gravity is the curvature of spacetime. In 1927, Georges Lemaitre proposed that the universe began from a primeval atom. In 1948, George Gamow predicted the cosmic microwave background radiation as an afterglow of the Big Bang. In 1965, Arno Penzias and Robert Wilson accidentally discovered that radiation, confirming the Big Bang Theory. In 1998, astronomers discovered dark energy through observations of distant supernovae. In 2015, gravitational waves were first detected. Each discovery opened new windows onto reality, revealing aspects of the universe we didn't know existed. Our understanding has grown exponentially in just a century, from believing in a static universe to mapping 13.8 billion years of cosmic history. Let your thoughts drift to the Voyager Golden Records, humanity's message to the cosmos. Launched in 1977, both Voyager spacecraft carry identical golden records containing sounds and images from Earth, greetings in 55 languages, music from diverse cultures, sounds of wind and thunder and whales, photographs of humans and landscapes. These records also include instructions for playing them and a map showing Earth's location relative to nearby pulsars. The Voyagers have now left our solar system, entering interstellar space, carrying these messages into the void. In 40,000 years, Voyager 1 will pass within about 1.6 light-years of a star called Gliese 445. Long after human civilization has evolved beyond recognition or ceased to exist, these spacecraft will continue drifting through the galaxy, carrying evidence that once, on a small planet orbiting an ordinary star, beings arose who wondered about the universe and reached for the stars. Now breathe gently and picture the James Webb Space Telescope, launched on Christmas Day 2021, the most powerful space telescope ever built. Positioned at 0.1 million miles from Earth, Webb observes the universe in infrared light, allowing it to peer through dust clouds and detect the most distant galaxies. Webb's first deep field image, released in July 2022, shows thousands of galaxies in a patch of sky no bigger than a grain of sand held at arm's length. Some of these galaxies existed when the universe was only a few 100 million years old. We're seeing them as they appeared more than 13 billion years ago, in the universe's infancy. Webb is revealing the first generation of galaxies, the earliest stars, the atmospheres of exoplanets, showing us aspects of the cosmos no previous telescope could access. We live in a golden age of cosmology, where new discoveries arrive constantly, each one refining our understanding, each one raising new questions. As you sink into the deepest tranquility, consider that the story of the universe is also the story of increasing complexity. From the simple uniformity of the early universe, just hydrogen and helium, evenly distributed, complexity has emerged through natural processes. Stars formed, creating heavy elements. Galaxies assembled. Planets coalesced. On at least one planet, chemistry became biology. Single cells became multicellular organisms. Life diversified, evolved, created ecosystems of extraordinary intricacy. Consciousness emerged. Intelligence developed. Technology arose. And now, here we are, the universe not only looking at itself but understanding itself, creating art and music and mathematics, asking questions about meaning and purpose, wondering why anything exists at all. This emergence of complexity from simplicity, this natural tendency toward greater organization despite entropy's increase, is one of the universe's most remarkable features. Here's something both profound and peaceful. The universe seems to exist at a special moment in cosmic history. We live when stars still shine, when galaxies are visible, when the cosmic microwave background is still detectable. In the far future, hundreds of billions or trillions of years from now, the universe will be much darker, much emptier. Galaxies will be so far apart that observers in one won't be able to see any others. The cosmic microwave background will have faded beyond detection. Future civilizations, if any arise, won't be able to reconstruct the Big Bang or cosmic history because the evidence will have disappeared beyond their observable horizon. We exist in what might be called the universe's bright age, when cosmology is possible, when the story of creation can still be read in the light reaching us from ancient times. In this sense, we are privileged witnesses, living at a time when the universe still reveals its secrets, still tells its story, still provides evidence of its own grand narrative. Rest peacefully now, knowing you exist at a special moment in cosmic history, when the universe is young enough to be observed, complex enough to be interesting, and filled with beings capable of appreciating unraveling its mysteries. Let yourself float through the gentlest currents of understanding, as we explore the final connections between cosmos and consciousness, between the infinite and the intimate. Drift with me now to consider the concept of cosmic perspective, how contemplating the universe changes how we see ourselves and our lives. When you understand that you're on a planet orbiting a star in a galaxy containing hundreds of billions of other stars, in a universe containing trillions of galaxies, problems that seemed overwhelming can suddenly seem more manageable. Not because they don't matter, your experiences, your joys and sorrows, are profoundly real and important, but because perspective helps. The universe has been unfolding for 13.8 billion years. It will continue for trillions more. Your worries about tomorrow, while valid and worth addressing, exist within this vast context. This perspective can be liberating, reminding us that we're part of something much larger, that our temporary troubles are just small ripples in an ocean of time. As you breathe slowly and peacefully, consider that every culture in human history has looked up at the night sky and created meaning from what they saw. Ancient Greeks saw heroes and monsters in the constellations. Indigenous peoples worldwide wove the stars into their origin stories and seasonal calendars. Medieval scholars tried to understand the cosmos through philosophy and theology. Modern scientists use mathematics and observation. Each approach represents humanity's attempt to understand our place in the universe, to find meaning in the vast darkness above us. While our methods have changed, the fundamental impulse remains the same. We are meaning-making beings, constantly trying to understand, constantly seeking connection between ourselves and the cosmos that surrounds us. Let your thoughts drift to the question of why there is something rather than nothing. This is perhaps the deepest question philosophy and physics can ask. The universe exists. We exist. But why? Why should anything exist at all? Nothingness would seem simpler, requiring no explanation. Yet here we are, in a universe filled with matter and energy, governed by laws, evolving through time. Some suggest the universe's existence is a brute fact, requiring no explanation, it simply is. Others propose that the quantum nature of reality makes nothing unstable, causing universes to spontaneously emerge. Still others see purpose or design. This question sits at the boundary of science, philosophy, and theology, reminding us that some mysteries may lie beyond our current ability to answer, that the universe still guards its deepest secrets. Now breathe gently and picture the scale of your own significance. You are one person among approximately 8 billion on Earth. Earth is one planet among trillions in the observable universe. Your lifetime is less than a century in a cosmos that will exist for countless eons. By these measures, you might seem insignificant, a tiny blip in space and time. But consider another perspective. You are a pattern of matter complex enough to be self-aware. You can contemplate the universe, create beauty, experience love, understand mathematics, appreciate music. You are, as far as we know, one of the vanishingly rare configurations of matter in the universe capable of conscious thought. In a cosmos where most matter is simple hydrogen floating in darkness, you represent extraordinary complexity, improbable organization, a small but remarkable triumph of the universe's tendency toward increasing complexity. You are both cosmically tiny and genuinely extraordinary. As you sink into deeper tranquility, consider the continuity between you and the cosmos. Your atoms were forged in stars. Your body operates according to the same physical laws that govern galaxies. The electrical impulses in your brain follow the same electromagnetic principles that power lightning and starlight. You breathe oxygen produced by ancient photosynthetic organisms, exhale carbon dioxide that plants will use tomorrow. You eat food made from atoms that have cycled through countless organisms before you. You are not separate from nature, not an observer standing outside the universe, but an integral part of it, a temporary eddy in the cosmic flow, a brief arrangement of stardust that happens to be conscious, experiencing itself. The boundary between you and universe is more fluid than it appears. You are the universe, temporarily organized in a particular way. Here's something both final and beautiful: the story of the universe is incomplete. We've learned extraordinary amounts in the past century, but vast mysteries remain. We don't know what dark matter is. We don't understand dark energy. We don't know if the universe is finite or infinite. We don't know if we're alone or if life is common. We don't fully understand consciousness, the origin of the universe, or ultimate questions of meaning and purpose. This incompleteness is not a failure but an invitation. Every mystery solved reveals new questions. Every answer opens new doors. The universe is not a finished puzzle but an ongoing revelation, and we are privileged to live during a chapter of that revelation. The story continues, the mysteries deepen, and the journey of understanding stretches ahead into a future filled with discoveries we cannot yet imagine. Rest now in complete peace, knowing you are part of this grand story, this ongoing cosmic narrative, this universe that creates consciousness so it can know itself. You are both witness and participant, both observer and observed, both temporary and connected to eternity through the atoms you're made of and the story you're part of. Let yourself dissolve into the deepest stillness now, as we bring our cosmic journey to its gentle conclusion, where all the threads come together in peaceful understanding. Drift with me now through one final thought: the universe is not just matter and energy obeying physical laws, but also beauty, wonder, and mystery. When you see a sunset, you're witnessing the scattering of light through Earth's atmosphere according to Rayleigh scattering principles. When you marvel at the Milky Way stretching across a dark sky, you're seeing photons from hundreds of billions of stars, some traveling for thousands of years to reach your eyes. The rainbow after a storm, the aurora dancing in polar skies, the twinkling of stars, all have scientific explanations. Yet understanding the physics doesn't diminish the beauty; if anything, it deepens it. Knowing that you're seeing light that has traveled across vast distances, that your witnessing process is governed by elegant mathematical laws, that you're part of a universe that creates such wonders, this knowledge adds layers of meaning to the aesthetic experience. Science and poetry are not opposites but companions, two ways of appreciating the same magnificent reality. As you breathe slowly and peacefully, consider the privilege of existing now, in this particular cosmic moment. You live after the first stars formed, after heavy elements were created, after planets coalesced, after life emerged and evolved. You exist in a universe old enough to be interesting but young enough to still shine with stars. You were born on a planet that orbits a stable star at exactly the right distance for liquid water, with a large moon that stabilizes its tilt, with a protective magnetic field, with an atmosphere that shields you from radiation while allowing light to pass through. The chain of improbable events that led to your existence, from the Big Bang to the formation of your solar system to the evolution of life to this very moment, is staggeringly unlikely, yet here you are. Every moment of your existence is a gift from 13.8 billion years of cosmic history. Let your thoughts drift to the realization that in contemplating the universe, you change it. Before consciousness evolved, the universe existed but went unobserved, unappreciated, unknown to itself. Now, through you and others like you, the universe has developed the capacity to observe its own existence, to understand its own laws, to marvel at its own beauty. Your consciousness, your awareness, your capacity to understand, these are not separate from the physical universe but are properties that emerged from it, natural consequences of matter organizing into sufficiently complex forms. When you think about the universe, you are the universe thinking about itself. When you feel wonder at cosmic scales, you are the universe experiencing wonder at its own nature. You are not in the universe, you are of the universe, an integral expression of its creative potential. Now breathe gently and picture all of human achievement, every discovery, every work of art, every act of kindness, every moment of love, as part of the universe's story. The first humans who looked up and wondered about the stars, the ancient astronomers who tracked the planets, Galileo turning his telescope skyward, Einstein imagining riding a beam of light, the engineers who built spacecraft, the scientists who decoded the universe's history, all were the universe coming to know itself, using human consciousness as the instrument of discovery. And this process continues. Every child who asks why, every student who learns about atoms or galaxies, every person who pauses to appreciate a starry night, all participate in this grand project of cosmic self-understanding. You are part of a story much larger than your individual life, a story of matter becoming aware, of the universe awakening to its own existence. As you sink into the very deepest peace, let yourself rest in the ultimate paradox: you are simultaneously insignificant and infinitely precious. Insignificant because you occupy a tiny corner of space for a brief moment of time, one pattern among countless trillions. Infinitely precious because you are conscious, aware, capable of experiencing beauty and understanding truth, able to love and wonder and question. The universe created you, through billions of years of stellar fusion, planet formation, chemical evolution, and biological development, so it could experience itself, so it could know what it's like to be. Your experiences, your thoughts, your feelings, these are the universe's experiences, thoughts, and feelings, expressed through the temporary pattern that is you. When you eventually return your atoms to the cosmos, your pattern will dissolve, but the atoms continue their journey, perhaps someday becoming part of new stars, new worlds, new forms of consciousness yet to emerge. Here's the final thought to carry you into dreams: the universe is not a cold, mechanical place where we exist as accidents or intruders. It is a place where complexity naturally emerges, where life arises, where consciousness develops, where understanding grows. You are not separate from the cosmos but are one of the ways the cosmos manifests. The same laws that govern the motion of galaxies govern the firing of neurons in your brain. The same atoms that float in interstellar clouds make up your body. The same energy that powered the Big Bang flows through you now as the warmth of your breath, the beating of your heart. You are woven into the fabric of reality itself, inseparable from the whole, essential to the story, brief but beautiful, temporary but meaningful, a small but necessary part of the universe's grand journey from simplicity to complexity, from darkness to light, from unconsciousness to awareness. Sleep now, completely and deeply wrapped in the knowledge of your cosmic heritage. You are stardust that has learned to wonder. You are atoms that have organized themselves into consciousness. You are the universe experiencing itself, if only for a brief, bright moment. Rest peacefully in this understanding, knowing that when you wake, you will still be part of this magnificent cosmos, still connected to everything, still participating in the greatest story ever told, the story of the universe itself. Good night, fellow traveler. Good night, cosmic child. Good night, stardust. Good night, universe. Sleep well in the embrace of stars and time and the infinite mystery that holds us all. The cosmos continues its patient unfolding, and you are part of it, now and always, in this moment and beyond, forever woven into the eternal fabric of existence itself. Rest. Peace. Sleep.